Hello, my name is Jim Jimzewski. I'm a nanoscientist. I'm also a professor at UCLA, and I work in the California Nanosystems Institute, which is one of the largest nanotechnology institutes in the world. Prior to being at UCLA, I actually worked in IBM Zurich Research Laboratory, which is a very famous lab for nanotechnology, and I started there in '83. So I have something like 35 years experience in nanotech. And today I'd like to present an introduction to nanotech, not only from the perspective of, say, science, but from its potential to change the world in terms of social and economic types of values. And the lecture will really show its history, the history of nanotech, how nature does use nanotechnology. This is something we've just discovered fairly recently. And various topics like, for instance, nanotechnology, its impact on energy, food, agriculture, electronics. In fact, you name it, almost every aspect of science and technology is somehow impacted by nanotechnology. It's a very broad field. Nanotechnology, actually, the word nano is from the Greek for dwarf, but in science, it refers to a billionth of a meter. It's a very, very small dimension. And generally, in nanotechnology, some critical dimension is on the scale of 1 to 100 nanometers. Now, that does not mean that a device or the system is on that scale. It could be much larger. In fact, it could be, kilometers, but it could involve this critical dimension of 1 to 100 nanometers somewhere inside it. And the word was originally coined by Norio Taniguchi, who was at the Tokyo University of Science. And he used this term in 1974 at a conference. But he was actually talking about something a little bit different. He was talking about very, very thin films deposited on things. And the type of thin films I'm talking about are, for instance, like the coatings that are used for glare reduction on camera lenses or glasses. Now, for those who cannot relate, say, nano to themselves because it's so small, we could try to relate nano to an atom. This is a chemist's view of an atom. And inside of the atom, there's things called neutrons and protons. And then on the outside, we have a kind of cloud, which are called electrons. So the size of an atom is actually governed by the size of the electron cloud. And when we talk about nanotechnology, for instance, we say a billionth of a meter, which is a nanometer. We start to use a scale that's not just the simple 1, 2, 3, 4, 5, 6, 7, 8 linear scale. We actually work on a scale which is powers of 10. So for instance, 10 would be 1, 100 would be 2, 1,000 would be 3, and so on. And if you take 1/10, it would be -1. So 10 to the -9 means 1 over 1 with essentially 9 zeros. And that is the scale. So on this thing, you can see an example of a logarithmic scale. And the diameter of an atom is much smaller than a nano. It's about 1/10, approximately, of the size of 1 nanometer. So you get 10 atoms, in a straight line. So when we think of the powers of 10 scale, we can make a kind of little drawing here where we go from a water molecule, which is about 1/10 of a nanometer. That's 10 to the -1. Up to a sugar molecule, it's about 1 nanometer. Antibodies are about 10. Viruses are about 100. And that would be more or less nanoscale. And then you go on to the microscale, which is a bacteria. A bacteria is approximately a micron, about 50th of the diameter of human hair, and it is 10 to the 3 or 1,000 nanometers. And cells in your body are about 10 to the 4 nanometers. And a tennis ball is 10 to the 8. That means 100 million nanometers. So that's the top line. If we look at the bottom line, we see the kind of scales of devices we deal with in nanotechnology, things called for instance, quantum dots, nanotubes, and so on, that I'll describe to you a little bit later. One good way, and it's a pretty simple way, is to think of the thing in scales of 1,000. So 1,000 times smaller, 1,000 times smaller, and 1,000 times smaller. So if we take a human body, it's approximately meters, about 2 meters. And then we go down 1,000, we would come to the scale of an ant. Down 1,000, we'd come to the scale of your red blood cells, for instance. And down 1,000, we would come to the scale of a nanometer, things like viruses or, for instance, carbon buckyballs that we'll talk about. Now, if we take a historical perspective of technology, there are two approaches. One is where we look at objects that were made in technology and we plot them here as a function of time. This is again one of these scales of 1,000. And one type of device are electronic devices. Electronic devices started quite large. They were on the size of your hand, the individual components. And throughout time, they became smaller and smaller. And they're made essentially by taking a piece of silicon and etching it and hacking away at it. And we call that approach top-down. And the top-down approach has come down to the scale of a nanometer. On the other hand, if we consider chemistry, chemists originally made very simple molecules. And as time went on, they were able to make more complex molecules, which made them bigger. And the types of molecule many chemists deal with today have the scale of nanometers. So this top-down technology and bottom-up chemical technology have intersected. And where they intersect is actually on the kind of critical scale lengths that nature uses. For instance, in your body, in every cell, you have nanometer structures in very complex patterns. The conceptual origins of nanotechnology are often attributed to Richard Feynman, even though Richard Feynman did not actually use the word nanotechnology. But in 1959, at Caltech, he gave an interesting talk called "There's Plenty of Room at the Bottom." Richard Feynman is a very colorful physicist. He worked on the atom bomb, the Manhattan Project, and he got a Nobel Prize for his work in quantum mechanics, but he had a sense of humor. And in this talk, he suggested that on the atomic scale, we have so much room to make tiny things that this could be a new form of technology that could change the world. And in fact, he was completely right, because the microelectronics revolution, computers and so on, was just about to take off. A little bit later, this would be more in the 80s, Eric Drexler, who was actually a student of Marv Minsky, the father of artificial intelligence, became interested in nanotechnology, and he had listened to Richard Feynman's talks. And he proposed a different type of vision of nanotechnology, which was a very engineering-based one. So rather than the stochastic, non-deterministic type of behavior of nature uses nanotech, he viewed nanotechnology of the future to be completely deterministic and mechanical. So 40 years ago, Feynman delivered a lecture. And it's very interesting to read this article, "There's Plenty of Room at the Bottom." One of his many, many famous quotes was, "The principle of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom." Now this at the time seemed impossible. How could one possibly consider even moving an atom or touching an atom? And he also said, put the atoms down where the chemist says, and so you make the substance. So he was talking in this about the basic idea in nanotechnology that we can manipulate things on an atomic scale. And one of the challenges he made at that time was to write 25,000 pages of the Encyclopedia Britannica on a pinhead. Now, if you do the calculations and you had something the size of a nanometer, that would be the information bit, if you like, you find on a pinhead, you can write actually 260 million pages of the Encyclopedia Britannica. So there is plenty of room at the bottom. So that you imagine volumes and volumes of these books being on a pinhead. Another prize he offered was to make a tiny electric motor, which was 0.4 millimeters in each dimension. So you imagine something that's much thinner than, you know, your nail, is the thickness of your nail. And less than a year later, the first prize was claimed, and in 1985, the second prize was claimed. So I think that surprised them that, you know, these things could be actually done, because he was more a theoretician than an experimentalist. Feynman realized also some things that people failed to realize later, and that was, as we make things on the nanoscale, the laws of physics change. So what we call classical mechanics, as developed by Isaac Newton, changes into a quantum mechanical realm, and the rules of quantum mechanics dominate. And this is an effect we can use in nanotechnology, the quantum effect. Secondly, things like surface tension. For instance, a water droplet on a surface balls up, whereas in a cup it appears to be flat. Thermal energy jittering around small particles dominates over the gravity, the pull of gravity. For instance, colloidal particles in milk, it doesn't settle. That's due to thermal jittering. So we have new phenomena that dominate on the nanoscale, and the behavior of nanoscale objects can be used to create very new effects, like new forms of color, new types of chemistry, all sorts of things. Drexler's vision, on the other hand, was this engineering vision. And his book, which was popular, was called Engines of Creation, the coming of a new era in technology. And this type of approach, engineering approach, reduced down to the level of mechanical gearing. And what you see in this animation here is a Drexler-like bearing. And so the idea is you take everything and, you know, shrink it down to the size of a molecule, and there you've got it. However, Drexler and Ralph Merkle kept going. Ralph Merkle was a colleague of Drexler, and they formed an organization called the Foresight. And in that organization, they came up with different ideas. And one was the idea of an assembler, like the Ford assembly plant on the molecular scale. And what you see on the left is an example of an assembler schematic, which has arms that pick up molecules and put the molecules down where you want them. And the idea was this thing is like a microwave, and you can put dirt in it and essentially reassemble the atoms into a hamburger. Now, the law of physics is not necessarily against that. I mean, cows do that. You have dirt, you have grass, you have cows, you have hamburgers. But this type of approach, if you think about it, that you have to position each molecule in the hamburger one by one, would essentially take billions and billions of years. So it's not very practical. Nevertheless, they continued with that approach. However, there was a debate. And that debate was between Smalley and Drexler. Now, Smalley, Richard Smalley, was one of the co-inventors or co-discoverers of the buckyball, a new form of carbon, a ball shaped like a soccer ball, in fact, which was exactly about 1 nanometer in diameter. And Drexler could not stand Smalley, and Smalley could not stand Drexler. And they had a debate, and it was published in Chemical Engineering News. There was also some articles in Science. And basically, Smalley said that Drexler's vision was ridiculous. And at this point, Drexler stopped talking about nanotechnology and retreated back from the field.